It's one of the things that people often are a little confused about is why dot products or cross products are useful. I thought it was maybe interesting just to give one example of using dot product to interpret what's going on with a given velocity in a given position or a given velocity in a given acceleration. So here's the sort of idea that I want to get at, which is this idea that what does it mean if, say, the position vector dotted with the velocity is 0? What does that tell you? What if the position vector dotted with the velocity is greater than 0? What does that mean? Or what does it mean if the velocity dotted with the acceleration is greater than 0, less than 0, or equal to 0? I mean, all of these things actually have some physical meaning, but it's not obvious what they mean if you're not used to thinking about the dot product from more of a sort of physical, what does it imply perspective. So let's think about the first example, r dot v is equal to 0. So let's start with a case that, and let's also think about not just r dot v is equal to 0, but r dot v is greater than 0, r dot v is less than 0. So here's an example. We've got some object that's located at some position r, and it's moving. It could be moving in any direction. Let's think about some possible directions. So one possible direction that it could be moving is just outwards, right? Or it could be moving in the x direction, or it could be moving in the y direction. It could be moving back in towards the origin. It could be moving up in this direction, up in this direction. It could be going anywhere. Well, which of these cases are cases where r dot v is equal to 0? Well, if you remember, when the dot product is equal to 0, that implies the two vectors are perpendicular, right? So if the velocity were in this direction, that would imply that r dot v was 0. And also if the velocity was in this direction, that would imply that r dot v was equal to 0. Okay? And for which vectors is it the case that r dot v is greater than 0? Well, r dot v is going to be greater than 0, so the dot's greater than 0 if r and v are closer to parallel than anti-parallel. So if some part of v points in the same direction as r. In other words, if the angle between them is less than pi over 2, or is between minus pi over 2 and pi over 2, the dot product will be greater than 0. So for all of these velocities, the dot product is greater than 0. And finally, of course, any velocity that's sort of going in this direction, the dot's going to be less than 0. But what can we say if the dot product is greater than 0? What the dot product being greater than 0 tells you is actually that the object is moving away from the origin, right? If you think about any of these cases where the dot product is greater than 0, that means that this point is going to be getting further away from the origin. In fact, r dot v greater than 0 implies that the magnitude of r is increasing, right? In other words, the object is moving away from the origin. Similarly, if r dot v is less than 0, that implies the magnitude of r is decreasing. That is, the object's moving toward, getting closer to the origin. And finally, when r dot v is equal to 0, that means the magnitude of r is staying the same. Okay? And it's pretty easy to see that with r and v, because it's easy to imagine an object sitting here and either moving out away from the origin, moving sort of perpendicular to the current position, and so therefore moving in a way that doesn't change the length of r, or moving back towards the origin and making the position vector shorter. And if we extend that to velocity, you can actually think about what that means as well. When you've got a velocity dotted with an acceleration, what does it mean if that's greater than 0? Well, if we simply make the transfer here, it means that the magnitude of the velocity is increasing, right? And if you actually try to draw a picture that captures that, let's say I've got some object that's moving in some velocity, any acceleration that is pointing in some way partially forward is going to be an acceleration that yields an increase in speed, right? So the magnitude of velocity will increase. If the velocity dotted with the acceleration is less than 0, of course, it's the object is slowing down. So the magnitude of velocity is decreasing. And finally, when the velocity dotted with the acceleration is equal to 0, that means that the magnitude of the velocity is not changing. The only thing that's changing is the direction of the velocity. In the same way that here, when the velocity is just perpendicular, what's happening is that r is just changing its orientation, but it's not changing its length. Here, the speed is not changing, but the direction that the object is moving is changing. One sort of helpful way to extend this is to think about how acceleration plays out with regard to velocity. Right? And so if I have some velocity vector, I could think about two sort of interesting directions. One interesting direction is v hat, right? A vector that's perpendicular, that's parallel to v. And another vector that I could define, I'm just going to call it n hat. So it's a vector that is normal to v. Obviously, if I were in 3 dimensions, there are multiple vectors that are normal to v. I can imagine a whole plane of vectors that are perpendicular to v. But since we're in 2 dimensions, there are only 2 vectors that are perpendicular to v, and they're the same within a sign. Okay, so if I think now about what a dot v is, what that's actually asking is sort of how much of a points along v. And in fact, if we're more explicit about that, if we actually said a dot v hat, that would actually tell me what the component of the acceleration is that's along the velocity. So a dot v hat tells you how much the object is speeding up, right? A dot n hat is what you might call the perpendicular velocity acceleration. It's how much of a is perpendicular to v. Notice that another way to write a dot n hat is actually to say, okay, well, the acceleration must be equal to however much acceleration is parallel to the velocity, plus however much acceleration is perpendicular to the velocity, right? So this part is simply a dot v hat. If we call this a perpendicular, and this a, then it's pretty clear that a perpendicular is simply the original total acceleration minus however much acceleration is in the v hat direction. Then I have to multiply by the v hat direction because this is just the magnitude of the acceleration in the v hat direction. So now I'm sort of thinking about resolving this acceleration. So here's my velocity, here's my acceleration, right? My acceleration has 2 components, a parallel and a perpendicular. The magnitude of a parallel is simply a dot v hat, and the magnitude of a perpendicular is a dot n hat, which is the same thing as a minus a dot v hat times v hat. Let me move that so you can see it. So why am I doing this? Sometimes I wonder myself. But the reason I'm doing this is that when you think about it this way, you can actually think about what the 2 parts of the acceleration mean, right? The acceleration consists of 2 chunks, right? One chunk is the chunk that is parallel to velocity. The other chunk is the chunk of whatever's left over that is perpendicular to velocity. A parallel is the chunk that causes speed to change. A perpendicular is the chunk that causes turning. And I hope that helps a little bit, at least make a connection between this sort of idea of dot products, this idea of unit vectors, and how you can actually get some insight by using dot products and unit vectors. One way to get that insight is if you take a dot product of the acceleration with the velocity vector, you get a sense of whether the object is speeding up or slowing down.